Section 4.1, we're continuing on with derivatives, learning some techniques that'll actually save us a lot of time and make finding the derivative so much simpler than the limit rules. So here's a few rules. If f of x equals k, then the derivative is equal to 0. So in other words, think of a horizontal line, right? F of x equals k is some sort of horizontal line where our slope is 0. So if f of x is equal to a constant k, then the derivative will always be 0. If f of x equals x squared, then the derivative of x is equal to 2x. If we think of x squared is a parabola where we go from a negative slope to a positive slope, changing at x equals 0. The line y equals 2x is a line like so. I'm not sure where the intercepts are. You'll have to, this is just a general graph. So we're going from a negative slope where we're below 0 to a positive slope like so. And lastly, if we have f of x equals x cubed, our derivative will happen to be 3x squared. And we could continue this if we wish. F of x equals x to the fourth. Then the derivative would be equal to 4x cubed. Okay, so for in general, if we have f of x equals x to the n power, then the derivative is equal to nx to the n minus 1. So we take the exponent and multiply it in front, and then we decrease the power of the exponent by 1. Okay? If f of x equals k, a constant times g of x, then the derivative is simply equal to the constant k times the derivative of the function. So in other words, the constant k will just stay up front. Okay, so we could take the general derivative like here, but then keep the constant out front and multiply it. If f of x equals u of x plus v of x, so two functions added to each other, they have the proof here, but in other words, we end up just with the derivative of u of x plus the derivative of v of x. So if you plug this into our limit equation that we had before, the instantaneous rate of change, as h is going to 0, this should be an h in the denominator, by the way, you get u of x plus u prime of x, the derivative of u plus the derivative of v of x. Okay, same thing if you have f of x equals u of x minus v of x. If you do the same kind of limit proof, you will get the same type of thing. The derivative of u of x minus the derivative of v of x. Apply our rule here where we multiply the exponent in front and then decrease the exponent by 1. And then our sum and subtraction rules here just show that we can add and subtract the derivative of each individual. Okay, so this makes it so much simpler to find the derivative. So for this example, y equals 8x cubed minus 5x squared minus x over 12. Just for clarification, we could write this as minus 1/12 x. Excuse me, this should be 1/12 x. Then we're going to a part of this polynomial. So when we take the derivative, y prime, we multiply this exponent in front. So we would have 8 times 3, and then we decrease the exponent by 1. Subtract 1 from the exponent. And we're going to do that for each term individually. Now, notice when we get to the end, this exponent only has a 1. So we're multiplying the 1 in front, and then we're decreasing the exponent by 1. So 1 minus 1 is actually going to be 0. But going back to the beginning, we have 8 times 3 is 24. 3 minus 1 is 2. So we get 24x squared. Negative 5 times 2 is negative 10. 2 minus 1 is 1. So we'll just leave negative 10x. And then lastly, we have negative, I keep writing 1/2, it's negative 12, 1/12, excuse me, negative 1/12, x to the 0. Remember, x to the 0 is just 1. So negative 12 times 1, we just get negative 1/12. Okay, so this is our derivative. Now, if you use the limit equation that we learned in the past, you should get the same answer. However, this is so much faster, and this is what we're going to be using for the rest of the semester to find a derivative. Okay, another example. One thing to keep in mind is that the square root of x is equal to x to the 1/2 power. So if we write it as an exponent, we can use our same rule we just discussed. So let's rewrite this. 8x to the 1/2 plus 6x to the 3/4. Okay, when we take the derivative, we do the same thing. We multiply the exponent in front and then subtract 1 from our exponent. Okay, so the 3/4 and the 1/2 are getting multiplied in front, and we are subtracting 1 from each of the exponents. As we simplify that, we have 8 times 1/2 is 4. 1/2 minus 1 will give us a negative 1/2. 6 times 3/4. The 6 and the 4 can simplify to be 3 over 2, so we get 9/2. X to the 3/4 minus 1. 3/4 minus 4/4 would be negative 1/4. Now you can leave your answer written like this, or we can write it as radicals. So notice x to the negative 1/2, the negative exponent means it moves to the denominator, and the 1/2 exponent means it's square root. So we have 4 over the square root of x. The next one we have 9, the 2 is in the denominator as well as the 4th root of x. Our next example, we'd also like to rewrite a little bit to make it easier to find our derivative using our new rule. So if we write this instead as 7t to the negative 1 minus 5t to the negative 3, we can see how to apply our new derivative rule much simpler. Okay, so we're still going to multiply our exponent out front. So we have 7 times negative 1, and we're still going to subtract 1 from the exponent. Nothing's changed, but now we do have to worry about that negative. And we will do the same thing with our second term. We multiply the exponent in front and then subtract 1 from our exponent. I did not make our derivative mark here, so this is the derivative, f prime of t. So if we simplify this, we get negative 7t to the negative 2, negative 1 minus 1, plus negative 5 times negative 3 is a positive 15. T negative 3 minus 1 is a negative 4. And last step, we would want to move these negative exponents to the denominators, like so. And this would be our derivative. Our next example in your course notes, part D, is p of x equals negative 10, x to the negative 1/2 plus 8x to the negative 3/2. So we're going to continue in the same fashion. We multiply the exponent out front, and then we subtract 1 from our exponent. So regardless of whether exponent is positive or negative or a fraction or a whole number, we follow the same pattern. Next term, we multiply negative 3/2 out front, and then again, we subtract 1 from the exponent. Okay, so as we simplify this, we have negative 10 times negative 1/2, which is positive 5. Negative 1/2 minus 1 will give us negative 3/2. 8 times negative 3/2, well, 8 divided by 2 is 4. So 4 times negative 3 gives us a negative 12. And then negative 3/2 minus 1 will give us negative 5/2. Last step, we can put our negative exponents back in the denominators. It's not required, especially as you see the original problem has negative exponents in it. That should be positive there. It's not required, but if you would like to, you can. Either way is fine. Find the slope of the tangent line to the graph at the given value of x. So remember, the slope of the tangent line is found from the derivative. The derivative is the instantaneous rate of change or the slope of the tangent line at a specific point. So they're giving us an x value. So in order to find the slope of the tangent line, we want to first find the equation for the derivative. And then after that, we're just going to plug in the specific point given, x equals 2, and find the y value at that point. That will be the slope of the tangent line at this x value. So we're going to follow the same pattern we've been doing. So we have a negative already out front. We multiply our exponent in front, and then subtract 1 from our exponent. Same thing here, multiply the exponent out front, subtract 1 from the exponent. So we get, if we simplify this, we have positive 3x to the negative 4 minus 2x to the negative 3. So we want to plug in, we're going to substitute x equals 2 into our equation. So we would get 3 times 2 to the negative 4 minus 2 times 2 to the negative 3. Okay, so if we move these to the denominator, we have 3 over 2 to the 4th minus 2 over 2 cubed. So we have 3 over 16 minus 2 over 8. If we want to find a common denominator, we multiply this by 2 in the numerator and denominator, getting 3/16 minus 4/16. So the derivative at x equals 2 is equal to negative 1/16. Okay, find all the values of x where the tangent line is horizontal. Find all the values of x where the tangent line is horizontal. Okay, so when we're looking for the tangent line, again, that clues us that we are looking at the derivative, right? Whenever they say slope of the tangent line. Okay, now also remember a horizontal line. So the tangent line will be horizontal where our slope is 0. Right? Where slope is 0, the tangent line is horizontal. So what we want to do is find the derivative, and then we want to find where that derivative is equal to 0. Where is the slope equal to 0? And then we can solve for x. So we're going to find our derivative the same way. So I'm going to move a little bit quicker here as we do this. So we're multiplying the front by the exponent. So 2 times 3 is 6. Decrease the exponent by 1. 3 minus 1 is 2. Second term, 9, we're going to multiply it by the exponent, 2 in front, so we get 18. Decrease the exponent by 1. 2 minus 1 is 1. Next term, again, we have an exponent of 1 since it's not written. So negative 60 times the exponent of 1 will be negative 60. And then we're going to decrease the exponent by 1. So x to the first, so 1 minus 1 is 0. X to the 0 is equal to 1, so the x is gone. We just have negative 60. The derivative of any constant, 4, is just 0. We discussed that at the beginning of this section 4.1. Okay, so now we want to know where our slope is 0. So we're going to set this equal to 0. So we have 6x squared plus 18x minus 60 equals 0. Let's simplify these. We see that each of these coefficients is divisible by 6. So let's divide both sides of our equation by 6 just to make it a little bit easier to deal with. We get x squared plus 3x minus 10 is 0. We can factor this quite quickly, actually. We would have x plus 5 and x minus 2 is 0. So we get x equals negative 5 and x equals 2. So at these x values, The slope of the tangent line is horizontal. Our next example on page 33 of your course notes is a little bit different. It is y equals 3x to the fifth plus 9 all divided by x cubed. Now, this is not a polynomial written in the same form that we've been looking at so far when we find the derivative. And we don't have a rule for the quotient yet. It's coming. But we can rewrite this, breaking up the term in the numerator into separate terms. So divide each of the numerator terms by the denominator and simplify. We would get 3x squared plus 9 over x cubed, which, as we've learned before, we can write as 9x to the negative 3. So this is another way of writing y. And when we write it in that form, we can take the derivative like we have been doing this lesson. So multiply the exponent out front, decrease the exponent by 1. Same fashion that we have been doing. And then simplify. We have 6x minus 27x to the negative 4. It's not necessary, but we can rewrite it so that our negative exponent is positive by moving it to the denominator. Our last example comes from page 33 of your course notes. It says, consider a ball dropped from 188 feet above the ground at time t. The position of the ball at time t is given by the function, there's a typo here, s of t equals negative 16t squared plus 188. What is the time and velocity of the impact? Note that the velocity function v of t is the derivative of the position function. Okay, first let's find the derivative of this. So the derivative of the position function is equal to the velocity. Velocity is related to speed. Okay, so how fast is this moving at a specific time? So again, we're going to multiply the exponent out front, decrease the exponent by 1. Notice the derivative of 188 is 0. So if we simplify this, we get v of t equals negative 32t. Okay. Now, we're asked two things. What is the time and the velocity of the impact? Okay, now the impact is when we are hitting the ground, right? So we want to know at what point is the position equal to 0, in other words, right? The impact or position is on the ground. S of t equals 0, okay? Because we're dropping it from 188 feet. So we're dropping it high into the air. So the S of t is equal to how many feet from the ground we're at a specific point in time. So if we want to know when it's impacting, we want to know when the position is 0 feet from the ground. So S of t equals 0. So if we answer that question first, we'll come back to the other part. We would have 0 equals negative 16t squared plus 188. Subtract 188 from both sides. So then we're going to divide both sides by 16. They're both negative, so we have a positive value now. So t equals the square root of 188 over 16. Notice I ignored the negative, right? So usually when we take the square root of both sides, you'd have plus and minus. However, in this situation, we don't want the negative, right? Because we're not going to go below the ground, right? We want to know, and time cannot be negative. Sorry, this is time. So time cannot be negative. We can't go back in time to know when we're at ground level. So we're just going to take the positive value. So if we use our calculator, square root of 188 divided by 16, we get t equals 3.4. We'll do my writing's messy sometimes. We'll do 3 decimal places. So 428, 3.428. And this is in seconds, I believe. Let me see. You know what? It doesn't say, but Usually would be in seconds. It says feet at time t. Okay, so now we also want to know the velocity when we're hitting the ground, right? So the second part of the question, this is the first part, what is the position? The second question asks, what is the velocity at impact? Okay, so we plug in this time that we just found into our velocity equation. So we're going to plug in 3.428, and we get approximately, take the answer that's in your calculator and multiply it by negative 32, and we get approximately negative 109.690.